Again, my name is IgorGashinsky, and I'm a principal architect for Yahoo, and this presentation is Case for a New Approach to Networking in Warehouse-Scale Data Centers. So, first of all, what is a warehouse-scale data center? It's a large data center. About a year ago, we publicly said that our latest design at that point in time housed 120,000 servers. Again, that was about a year ago. These are pretty beefy servers. They're have up to 24 cores exposed to the operating system. Most of them are dual slot 6-core Westmeres, so hyper-threading, you get 24 cores. If you enable virtualization in the data center, you end up with, you can easily have 20 VMs per server, and given up a couple to the hypervisor, to the vSwitch, or whatever you have, that is 2.4 million VMs in a single data center. That is if you virtualize it. A warehouse-scale data center also has a massive amount of east-to-west bandwidth. It is highly distributed. There's a massive amount of crosstalk. If you think about a case of Hadoop, if a Hadoop cluster is 20,000 nodes, that is not, some host talking to some other host. That is 20,000 hosts talking in a full mesh between each other. That is pretty different from a typical enterprise data center where you have an app server talking to a web server and a bunch of clients connected to it. Other attributes of warehouse-scale data centers is that they're not just built willy-nilly. These are very large systems, very complex management of them. We have inventory management systems that actually know everything about the data center, or as much as we can. We have a graph of network elements, so we know exactly how they're connected. It's not arbitrary topologies. We know where every server physically is in the data center. We know every rack position. We know every wire that goes into the server and where that wire goes to. We obviously know the IP address of every server because we had to add it to DNS. We also know the MAC address of every server because, well, we can get that from vendors. We can log into it pretty easy. And in order to actually pixie boot a server, you need to know the MAC address of the server in order to know what IP to give it to, in order to know what role the server is going to be in the data center. So again, the attributes are very large, a lot of east-to-west bandwidth, and we know quite a bit about the internal topology of the data center. So one of the problems facing warehouse-scale data centers has been topology discovery. What you have today is that if you look, the routers are spending about 30% of their CPU doing nothing but redoing that topology discovery that we actually have in our databases. They're doing ARP and MAC binding discovery very often every 30 seconds for every node in the data center. On top of that, they're then doing ISAs, OSPF spanning tree, rapid spanning tree, trill, SPB, you name it, in order to figure out where the topology recursively resolves to. Well, that's highly inefficient, especially since I already have all this in the database. And a lot of data center architecture challenges and changes in the past several years, we've actually had to push out the L2, L3 boundary very close to the server for no other reason than that was the only way to scale. It wasn't that we architecturally believed that to be the better solution, it just that was the only way to make things work. And with software-defined networking, we don't need to do that anymore. Since we have all this in the database, and SDN provides a very nice, clean API separation for how we can send from the database right into the network, why don't we just program it and not bother doing this discovery? And we don't need to program everything. We could simply say, ARP and MAC, that stuff is easy, those bindings rarely change. Even with virtualization, when you have VM ability, a virtualization controller knows exactly where the VM was, where the VM is going to, so the virtualization controller also knows all this information. We can easily program it. Topology discovery, that could be debated whether that's better done as a distributed system, or as a centralized way, or a hybrid of in between. But at least, I don't know of anybody who argues against ARP and MAC binding being programmed from a central place. So otherwise, let's be honest, we're doing this to make things cheaper. So today, as I'm sure you've seen in all the previous talks, a switch has a control plane that you buy from a vendor, a management plane that takes the information from the control plane and pushes that into the forwarding plane. All that is one monolithic box. Well, that's not very cost effective. If a new vendor comes to me and says, hey, I've got this new switch, it's half the price per port, it is 10x the density, it's awesome, have to go, I've never heard of you. How do I know that you get basic things like OSPF right? You wouldn't believe the number of vendors that come into us and say, hey, test out this piece of gear. And we tested and find out that they decided that in order to optimize SPF processing, they say there must be 100 milliseconds or some unit of time quietness between recalculations, at which point I know the network has converged and then I perform an SPF run. Well, as the number of LSAs in the network grows, you will get to a point where statistically that period of quietness will never happen. And we've seen that some piece of gear didn't run an SPF recall for 6 days. Because that becomes challenging to introduce new vendors. If you separate control plane from a management forwarding plane, you can keep the same control plane as you've had before and simply swap in a new vendor because it's simply a change of hardware. Similarly, you could keep all the hardware separately and swap in a new control plane. The other benefit is if you're buying bleeding edge products, stuff that big vendors just ship, we've had cases where a vendor comes out with a brand new hardware platform and hardware absolutely rocks. But there's this, every new hardware platform requires a new version of code, and that new version of code has a problem with a control plane. And we wait for 18 months for an unrelated control plane problem to be resolved before we could actually introduce a new piece of hardware. SDN clearly has advantages in both the current vendors and new vendors as a way to rapidly introduce new hardware into a data center ecosystem. Also, another advantage of SDN is automation. Today, anybody of large size has pretty powerful configuration templating tools. I mean, we've created our own language around routing policies and that kind of stuff. And then those templating tools have config generators that can translate the template into every vendor-specific speak. And then we have configuration deployment tools that push them out. Well, the templating tools are great. The configuration deployment tools are awful. Honestly, they're expect. For anybody that played with expect, that is a very, very, very bad way to actually push configuration. But it's one of the few ways that we actually have. And then you also run into issues of, I've pushed it via expect, but then 30 lines of config just didn't make it into the box. So you have to have very complex systems to make sure that what you actually trying to push out made it there intact, and etc. With software-defined networking, it's a general API. It makes things easy to actually push. And if the general API is abstract enough, you won't even need the config generators that will do translation from the template into the particular syntax. Again, it makes introduction of new vendor, device, OS, whatnot, much, much easier. Also, it's a way to get faster innovation into the network. How many people have gone through this? You go to a vendor and you go, hey, we thought of this really cool thing that if we had it would make our life a ton easier. Can we get this new little feature, please? Because something has a limit of 32 and then you need to raise to 64. And the vendor goes and say, what? How much revenue will I get from doing this? At which point you have two choices. You go, I give you money, or you go, do this or I won't buy any more product from you, or you go, do this or I will take whatever spend I was going to give you, here's the PO that you were going to get, and I'm going to give it to your nearest competitor. At which point the vendor goes, that's nice, but you're too small, I don't care. Or the vendor goes, oh crap, they're serious, they've done this before. You'll get it in 18 months, which is about how fast we can turn a feature around with all the testing. Well, that creates a lot of conflict, and some people don't like the conflict, and even if you like that conflict, they're just not a good way of doing business. So what SDN will do is actually, by separating the control features from forwarding hardware features, it'll allow you to innovate much faster. It'll allow you to innovate much faster. It allows you to create the plugins for control plane without having to go to your vendor. And you can similarly get hardware improvements without having to change your control plane. You make things faster and the whole cycle becomes more rapid. Because right now, you need to wait for both to be right before you can make any change. By separating it out, it's a lot easier. And you have a chance to influence the entire system. If you wanted to change the way that you do forwarding based on different primitives, you can't do that with SDN. We had an idea of like a new forwarding architecture that was based on source map or destination map rewrite. No software would support it, no hardware would support it. We were just hosed. If we could just go, well, we'll take care of the software, somebody else will take care of the hardware, we could actually get that feature in, and we might have actually had it by now. But without SDN, that's just not a right outlet. So that's basically how SDN is useful in warehouse scale data centers, and a lot of it has been going on for quite a while, and continuing this moving forward is a great thing. So, thank you.
We'll take questions afterwards, and next up is Mr. White.